I think I'm out of battery. I charged it. I guess not enough. All right, well. We'll go as long as we can go. Okay. That's it. All right, so a little technological difficulty. We'll try again next time. Okay, so let's just finish this up. So here, 0 is a potential problem, and then where else? 2 is a potential problem. So if it's continuous on the piece is good. It's just where the definitions meet. But that kind of goes back to limits, right? Use the correct and use right versus left as needed. So that kind of works with what we know about limits. All right. You're also going to have problems where you look at the graph. So if, here's an example of a graph. This is coming from page 122. And the actual, the points here don't, where the points are, I'm not really too concerned about. So where is it continuous? Let's talk about where it's not continuous. I'm looking for gaps, jumps, vertical asymptotes. Is it continuous through here? Yeah, it's a line. Is it continuous here at this point? No, because there's a jump. It jumps up. Is it continuous here at this point? Actually not. The limits make sense, but there's a hole in the graph there. So if I were trying to draw this, I would have to draw like this, lift my pencil, go over the hole, and keep going. So it's not continuous at the hole. Is it continuous here? No, there's a gap. So gaps are easy. Is it continuous here? No. The limit is one thing, and the actual value is another. So for continuity, you need the limit and the value to be the same. Could I move this point to make it continuous? If I had defined this because I got to define it any way I wanted to, I could take this point off, stick it in there, and now it's continuous. So that's something, yeah, I know, it seems kind of weird to be able to change the problem, but yes. Sometimes you can say, could you redefine it? Could you make it continuous? And that answer would be yes. Okay, so now let's look at, I just want to do one last example using domains, because you're going to have one of those on the assignment. So here's one that says, tell me where this function is continuous. Are we still black?
No, it's good.
I'm going to come around here. Try and zoom in. Okay, so where is this function continuous? Remember our list of continuous functions? This one was continuous with restrictions because there's a domain issue. So where is it continuous is the same thing as finding the domain. So how do I find the domain for this? Write an equation. So I know that this has to be what? The inside of the square root must be positive or 0. Square root of 0 is 0. So I'm going to write 11x minus x squared greater than or equal to 0. But now I know how to solve this. I solved this with a sign chart. Anytime you have a polynomial inequality, anytime actually you have any really inequality that's beyond linear, you can use a sign chart. Factor. Find out where it is equal to 0. And then I'm going to put those on the number line. It's important to keep that x equals 0, 1. That counts. And now, I just need to test points in between. Again, I like to put them in the factors. I find that so much easier. It's even easier if you want to get an actual number. It's easier to put them in the factors. So here, if I choose -1, I'll get a negative. Another, what do I get here? Negative, positive, right? So why don't you guys finish the sign chart? You finish yours, I'll finish mine. We'll come back and check and see what it is. So pick some values and sub them in and decide what you get. people listening at home can do the same. Okay, so I got minus, plus, minus. So where is my domain? I want it greater than or equal to 0, so that is all of that. It's everywhere there was a plus. So the answer finally would be that, or you could write it in interval notation. Okay. So this is really all I wanted to do on continuity. The only, that's really all I need. Okay, so now let's look. Now let's look at section 2.4. This is where we start to get to the interesting calculus material. So we need to know a little bit about limits to define derivatives, but once we've defined derivatives, we will leave some of this behind. So let's look at section 2.4. All right, so section 2.4. We're going to define what's called the derivative. But really, this section is all about slope. Okay, we're going to define slope. We're going to use algebraic definitions first, and then we're going to talk about calculus definitions. Okay, so algebra and calculus, we're going to have two pieces. So let's start with algebra. So remember, this is all about slope. Okay, so how do we define slope? We know how to do that. Anyone? Really? I know it's early. Come on.
y2 minus
Thank you.
y1 over x2 minus x1.
Yes. Sometimes we will write it this way, just to begin to introduce this sort of notation. Delta just means change in. Some of you may recognize that from chemistry, change in temperature, delta T. So delta just means change in. If I have defined y equals f of x, I can write this even one more way. I could put in, how do I find y2? Well, I just put x2 into the function. So I can do that. So we'll have f of x2, that's just the y value, minus f of x1, that's the other y value, divided by x2, x sub 2 minus x sub 1. Okay, so this should be very familiar. This is all just algebra. Okay, so let me introduce some new language, though. We said that this is slope. This is also average rate of change. If you want to know how fast you're going on average when you take a car trip, right? You see how many miles you've gone in an hour or in 30 minutes, and you do the math. That's because you know where you started and you know where you ended, and you just did the numbers from those 2 points. In the middle, you could have been speeding badly, gotten caught by the cops, come to a dead stop, sat there for 20 minutes, and then got back on the road, right? The average that you computed doesn't tell you what happened in the middle. So this is algebra. The other word we're going to use is secant. The secant line. The secant line connects 2 points on a graph. Any 2 points. So this is why it's algebra, because it is 2 points. When we get to calculus, it's going to be 1 point. That will become cool. So let's do a couple of examples. So example 1, find the slope of the secant line between x equals 2 and x equals 3. Secant line between x equals 2 and x equals 3 or x squared. Okay, so slope. For slope, what do we need? 2 points. Do I have 2 points? I've got the x values. Can I find the y values? Sure, so that I know that I have x equals 2 That tells me that f of 2 is 4. That's my y value. I know that x equals 3 tells me that f of 3 is 3 squared, 9. So this is just kind of review. So now I know that the slope is just the change in the y values over the change in the x values. Slope is 5. So what am I doing here? Let's draw a picture. So let's say this is 2. This isn't really what it looks like. I'm going to exaggerate so you can see. So let's say this is 2 and this is 3, and I've just drawn a line between them and found the slope of that line. So what if instead of just 2 and 3, what if instead I had the point x equals 2 and then a point really close to it? But let's say I didn't want to say how, I just close, so 2 plus a little. So let's look at that. So same setup. I'm going to leave that one there. Can I erase all of this? I'm going to leave up here. I write it up here. So that's just our definition of slope. I'm just going to leave that here. So now let's say we're using the same function, x squared. But now let's say my 2 points are x equals 2, like we started with. But now let's say the next one is just 2 plus h. Just 2 plus a little. So we're going to look at x equals 2 and x equals 2 plus h. Those are my 2 points. Everything's still the same. It's a slope between 2 points. So do the same thing. X equals 2 tells me that f of x is equal to 4, right? I just squared it. X equals 2 plus h. That's not a number, that's a variable. Can I still find f of x? F of 2 plus h, yeah. Plug it in. So I'm going to take this and put it in everywhere I used to have an x. So just use your parentheses. So f of 2 plus h is just going to be x squared, 2 plus h squared. This may start to look familiar. We toyed with this a little bit with difference quotients. We're going to finish that up today. Okay, so now let's go ahead and clean that up, multiply that out. 4 plus 4h plus h squared. You may want to write side by side factors in FOIL, but you should get to the point quickly that you're going to recognize this as a perfect square. So you know it's this term squared, and the middle term is the product of these times 2. Go ahead and get used to that pattern. Okay, so now I'm ready to find the slope, right? So the slope is equal to the y value, 4 plus 4h plus h squared, minus the other y value, divided by the second x value minus the first one. So far, so good? Clean up. So we know the 4's cancel. This is where if you had something more complicated than x squared, please use parentheses here because you're going to subtract the entire function. So you should expect canceling. So if you don't see lots of things canceling, then it may be because of this or because you didn't FOIL out correctly. Okay, and then here these cancel, so I'm going to get 4h plus h squared over h, 4 plus h. Why would I do this? Right, this doesn't really make a whole lot of sense to do just for kicks, because normally if I'm interested in the slope between 2 points, I know what the 2 points are. So to just say a second point that's a little bit past, why would I do that? Okay, and the reason for that is because now we're about ready to hit calculus. So we've done the algebra. Algebra is all about 2 points. Algebra is about 2 points. Calculus is about 1 point. So let's look again. Leave that one up. So the calculus word is derivative. Derivative is slope. It's a slope at 1 point. How are we going to get from 2 points to 1 point? We'll take a look at that. So the derivative, there's an important word we add to that. It's called instantaneous. Instantaneous slope. Or instantaneous rate of change. So slope, rate of change, derivative. Those should get connected in your mind as meaning the same thing. So instantaneous slope or instantaneous rate of change. So how do we get this instantaneous? How do we get to 1 point? And here's where we're going to use the difference quotient and limits together. So we've been doing the difference quotient, f of x plus h minus f of x all over h. And we see it's the same thing. This is just a slope formula. And this is the slope between 1 point and another point that's really close, just h away. How can I make these 2 points, basically, how can I make this second point move towards the first point, to the point where it lands right on top of it? What do I need h to be? 0. Do I know how to make something approach 0? Yeah, we've been doing limits, right? So I can look at this. I can say the limit as h approaches 0. So I've got these 2 points, x and x plus h, and as I let's say that I'm here, as I let this point get closer and closer and closer, eventually I'm going to have a line like that. So we're going to let h approach 0 using this difference quotient. So calculus then becomes about 1 point, not 2. We're letting the 2 points come close together so that they become 1 point. So it's instantaneous. Where's the other things I need to say? Oh, and then lastly, we define this line that touches the graph in 1 point with the correct slope. We call that the tangent line. So let's go ahead and write that down. Tangent line is the line that touches the curve at 1 point with the slope of the curve at that point. What do you need to find the equation of a line? Point and a slope. Slope is going to come from here, and then the point is just the point where you're at. Okay, so let's do some examples. Is it still taping? I heard a beep. Yep.
I think it's good.
Okay. Okay, so now let's look at if I wanted to find the instantaneous slope of y equals f of x equals x squared at x equals 2. You have 2 choices. So I'm going to come over here and just keep writing a list in here. So I have calculus, and just write the, you've already written this down, and just writing it over here for reference. So the limit of the difference quotient as h approaches 0. So I have algebra, 2 points, calculus, 1 point. If I wanted to find the instantaneous slope here, I have 2 choices. I can just find this with the general x and then plug in x equals 2 at the end. I have 2 pieces to do. I have the limit to do, and I have the x equals 2 part to do. You can do them in either order. I sort of prefer to do the general limit first because then I have a general answer that I can plug in any number I want to. If you plug in x equals 2 first, then it only works for x equals 2. Okay, so I'm going to recommend that we just do it this way, the general way. So let's look at that. So we need to find that limit. So let's go ahead and set it up. The limit as h approaches 0 of Now here, define this difference quotient. If you are not yet really solid on finding f of x plus h by itself, you need to write a separate line up here that says f of x plus h equals x plus h quantity squared, and go ahead and write all that out. Notice that I've written them one underneath the other. That's sometimes a good way to get the pattern right, so that everywhere I had an x, the x plus h goes in. So I'm going to multiply this out. So x squared, double that middle term, plus h squared. So that is this term here. That's f of x plus h. And now I need to subtract. So I've done this part here. I've got the limit written. I've got f of x plus h written. Now I need to subtract f of x. Well, what is f of x? X squared. Okay, so minus. And I'm just putting parentheses there. We don't need to this time because it's so simple, but just to remind you to do that if it's more complicated. And then divide the whole thing by h. You should see canceling. You should see canceling of everything that doesn't have an h in it, and then you should cancel with things that do, what will be left will have h's that will cancel. So you should expect canceling. If you don't see that, go back and check your math. So we know that these cancel. So now this is equal to the limit as h approaches 0 of 2xh plus h squared all over h. So go ahead and simplify that, like right on your paper now. And then I'll do, you do yours, I'll do mine, and we'll see where we end up. Maybe somebody's already done it. Really, I would like for you to be writing. And if you're done, that's cool, but if not, keep writing. For those that need, you can factor it out. Or this, you cannot cancel those h's, but if there's an h in everything, you can do that step by taking an h out of everything, but you can't just take an h out of two of them and leave the other one alone. If you're going to take an h out, it's got to be fair. Everybody gets it. So we'll have 2x plus h. So what's the first thing we do with limits? Plug it in. If I plug in h equals 0, what do I get? 2x. What does that mean? It's kind of weird. Is that weird? I don't know. It says that the slope, remember what was this? This was instantaneous slope. It's saying that the instantaneous slope changes depending what x is. Well, let's look at the graph. I think that makes sense. When you're down here at x equals 0, so you're coming down, it's negative slope, starts to shallow out, comes through here, and then starts to rise again. What's the slope down here? 0. If I plug in x equals 0, what do I get? 0. What's the slope over here at x equals -1? Just which way is it's negative. I put in -1, I get -2. If I put in x equals 10, I'm up here. I'm going up pretty steeply by that point. I plug in x equals 10, I get 20. So this makes sense. This does not have a continuous slope. It's negative, it comes through 0, and then it goes positive again. That's exactly what we get when we plug in here. So this is now like a formula for the slope at any point here. That seems kind of powerful. So anytime I want to know the instantaneous slope at any point, I just plug in there and I'm done. What you're really going to like is next week, we're going to ditch all of this and be able to write that down. It'll be much better. So this week we have to go the slope both way. So what was the original question? At x equals 2. So the instantaneous slope then is 4. 2 times 2 is 4. If I wanted the equation of the line, let's finish this. If I wanted the equation of the line, what would I do? Do I have enough information to get the equation of the tangent line? Remember, the tangent line is the line that touches at one point. I've got the slope. What else do I need? A point. Could be the intercept or could just be any point. I've got an x value. Can I find a y value that goes with it? Yes. Okay, so here's an important thing, and we're going to get to this in the coming weeks. If you want to know the y value that goes to x, plug in the equation for y. If you want to know the slope plug in the equation for slope. So this is where we're going to start next week, labeling our equations very carefully so that when we go to get a corresponding value, we use the correct equation. So here, I have this point, and I know that if x is 2, y is 4. Now I have a slope and a point, right? I can find the equation of y. Do we need to finish that? You got, I know most people want that answer. So we'll finish. Okay, so y minus 4 equals 4 times x minus 2. I like point slope. If you like the y equals mx plus b form, totally fine with me. Go that route. I just like this because then once I've solved for y, I'm done. So multiplying out 4x, I'll get minus 8 here, plus the 4 from the other side. If my graph were drawn a little bit more carefully, that would make sense. The y-intercept is going to be negative, and it's a positive slope. So far we have algebra, 2 points. This is the secant line. Calculus, 1 point, and this is called the tangent line. What else do we have? The other word that goes with secant is average. That makes sense, average between 2 points. The word that goes here would be instantaneous because it's what happens at an instant, 1 point, instantaneous. Okay, so we have 2 different sets of things. Questions so far? All right, so let me do just another couple of pieces of definition for the calculus part. A little bit of vocabulary and a little bit of notation. I've called this the derivative, and that's correct. So the instantaneous slope we do by finding the derivative. So the derivative is a noun. The verb is differentiating. So we differentiate a function to find the derivative. And we're also going to add, and this will come up in later weeks, differentiate with respect to. That tells us what variable we're using. So typically it's with respect to x. So if we have f of x and we differentiate with respect to x, that would be one thing. Okay, so we often add this, and this will become more clear as we go. The last thing I want to add is notation. Our primary notation to indicate what the derivative is f prime of x. So it's just a an apostrophe. So f prime of x is the derivative. Which is an equation for the slope of the tangent line. F of x is the basic function. So this derivative gives us slope values. F of x gives us y values. So it's important to, when you're going back to use the correct one. So we have f prime and we have f. Okay, so let's do a couple. All right, so I'm going to have you do one. So here it is, and then I think we would have time for word probably. Okay, so here's one. Find the instantaneous slope and the equation of the tangent line at x equals 1 or f of x equals 3x plus 5.